Have you ever imagined that simply observing an experiment could completely change the outcome? This is exactly what the famous Double Slit Experiment suggests to us. Behind a simple beam of light passing through two small slits, there is a world of possibilities that involves the profound nature of reality, the role of the observer, and even the connection with human consciousness. In this video, we will delve into the history of one of the most intriguing experiments in physics, learn about the quantum interpretations that surround it, and discover how scientists like Fred Alan Wolf and Amit Goswami, as well as the charismatic Dr. Quantum from the film Who Are We?, invite us to rethink what we call reality. Stay until the end and get ready to challenge everything you thought you knew about the universe. This is the Flower of Infinity channel. You are very welcome. Don't forget to subscribe and activate the bell to stay up to date with our content. At the dawn of the 19th century, an inquisitive English physician and physicist named Thomas Young carried out an experiment that would eventually reshape our understanding of light. This experiment, now famously known as the Double Slit Experiment, began as a simple demonstration of how beams of light interfere with one another. By shining light through two narrow slits onto a screen, Young observed a pattern of alternating bright and dark fringes, an interference pattern, that strongly suggested light behaved as a wave. At the time, this was a bold statement, for many prominent figures, especially after the work of Isaac Newton, believed that light was composed of tiny, billiard ball-like corpuscles traveling through space. Young's work unsettled centuries of assumptions and laid the groundwork for the modern conception of wave phenomena. Over a century later, the double slit experiment found renewed relevance with the emergence of quantum mechanics. Physicists realized that not only could light behave as a wave, but it also displayed particle-like characteristics in certain contexts, especially through the photoelectric effect that Albert Einstein explained in 1905. Soon, the wave-particle duality appeared not to be limited to photons, particles of light. Electrically charged particles like electrons, once believed to be quintessentially point-like, also displayed interference patterns when fired individually through two slits. This evidence suggested that at a fundamental level, nature defies the simplistic categories of particle or wave. Rather, quantum objects exist as something more elusive and multifaceted, described by probability waves in a mathematical formalism. The continuing investigations into the double slit experiment revealed a strange phenomenon. When detectors were placed to observe which slit a particle went through, the interference pattern all but vanished. In other words, it seemed that the very act of measuring or observing which path the particle took affected the outcome on the screen. This enigma has become a cornerstone of quantum theory, leading to the development of various interpretations, ranging from the Copenhagen interpretation, which posits a collapse of the wave function upon measurement, to the many-worlds interpretation, suggesting that all possible outcomes occur but in distinct branches of reality. Alongside these more philosophically inclined interpretations, such as those advocated by Amit Goswami and others, have gone so far as to propose that consciousness itself might play a direct role in the manifestation of physical reality. In the early 2000s, a film called What the Bleep Do We Know?, released in Brazil as Quem Somos Nós, brought the double slit experiment and the broader mysteries of quantum mechanics into mainstream popular culture. The film combined interviews with recognized physicists like Fred Alan Wolf and Amit Goswami, along with creative animations featuring a character named Dr. Quantum. Through these animations, the film dramatized the puzzling nature of quantum phenomena. A single electron, when unobserved, seems capable of passing through both slits simultaneously, forming an interference pattern much like a wave would. But once an observer checks which slit the electron passes through, the pattern collapses into two distinct bands on the screen, as if each electron traveled exclusively through one slit like a particle. The playful depiction by Dr. Quantum captured the public's imagination, leaving viewers to wonder about the role of human observation in shaping reality. The popularity of What the Bleep Do We Know was fueled by its bold attempts to link quantum mechanics and consciousness. Fred Alan Wolf, a theoretical physicist known for his accessible writings on quantum theory, appeared in the film advocating that the fundamental laws of physics might be incomplete without some mention of mind or observer. Amit Goswami, a professor emeritus at the University of Oregon, elaborated on these ideas in his own books, notably The Self-Aware Universe, proposing that consciousness is not merely an emergent property of matter, but is instead a fundamental aspect of reality that actively influences the material world. While these ideas remain controversial in orthodox scientific circles, they ignite continuous debates about the deep nature of observation, measurement, and human agency in quantum experiments. To understand how these popular, sometimes controversial views relate to the conventional scientific approach, one must review the historical progression of quantum mechanics and its interpretations. Physics as a discipline underwent a revolution at the turn of the 20th century. Max Planck's study of black-body radiation introduced the idea of quantized energy levels, 1900. Einstein's explanation of the photoelectric effect, 1905, further reinforced the particle-like nature of light, and Niels Bohr's model of the hydrogen atom, 1913, placed electrons in quantized orbits. Each step chipped away at the classical deterministic worldview that had dominated since the days of Newton. By the 1920s, Werner Heisenberg and Erwin Schrödinger contributed formalisms, matrix mechanics and wave mechanics respectively, that described quantum systems in ways that defied classical intuition. The Double Slit Experiment eventually emerged as a textbook demonstration of the puzzling quantum duality, bridging these theoretical developments into a single striking visual. When you consider the experiment from a purely experimental standpoint, the procedure is deceptively simple. You have a coherent source of electrons or photons. Let's consider electrons for the sake of variety. They are fired one by one toward a barrier that has two narrow slits. Behind the barrier there is a screen, or a detector, that registers where each electron lands. If you do not attempt to measure which slit the electron passes through, you discover, after many electrons, an interference pattern consisting of alternating dark and bright bands, or areas of low and high electron counts. This is reminiscent of water waves overlapping in phase or out of phase. Now, if you place a measuring device or sensor near the slits to detect which one the electron travels through, the interference pattern mostly disappears, replaced by two distinct clusters behind each slit, just as you would expect from classical particles. This radical transformation of the pattern is what spurs the question, why does measuring or observing which path the particle takes affect the final outcome? Physicists tried to distill the essence of the experiment into mathematical form. The Schrödinger equation, for example, describes how the wave function of a particle evolves over time. If an electron is not observed in which slit it goes through, the wave function effectively goes through both slits, creating a superposition of paths that yields interference. However, once a measurement is performed, the wave function collapses, in the Copenhagen interpretation, and the electron is found to have definitely gone through one slit or the other, destroying the superposition, and hence the interference. The mathematics underscores the wave-particle duality, but it also begs for an explanation of what precisely triggers the collapse. Is it the measuring apparatus, or the conscious observer reading the apparatus? The Copenhagen interpretation, historically associated with Niels Bohr and Werner Heisenberg, often states that the quantum formalism does not provide a literal picture of reality, but is rather a set of rules for predicting observation outcomes. Thus, to say the electron really went through both slits or really went through one slit is considered a misguided question in this viewpoint. Reality in the quantum regime is intrinsically probabilistic until measurement forces a definite outcome. In the film, What the Bleep Do We Know?, this idea is dramatized to emphasize that the observer's knowledge or consciousness might play a fundamental role. The film's presentation, while visually captivating, merges scientific explanation with speculative philosophy, extending beyond the standard interpretations typically taught in physics departments. Fred Alan Wolf, featured in the film, has written extensively about the implications of quantum theory for our understanding of mind and consciousness. He, like others working at the boundary of physics and consciousness studies, seizes upon the notion that quantum phenomena might be more intimately linked with subjective experience than mainstream physics is comfortable admitting. Wolf's perspective, sometimes labeled quantum mysticism by critics, suggests that the observer's mind is inextricably involved in the process of shaping physical reality. In more standard scientific discourse, the observer is usually viewed as any measuring device or apparatus that interacts with the quantum system, not necessarily a sentient mind. Hence, quantum observer effects do not require conscious beings, but can be triggered by a camera, a photo detector, or other instruments. Amit Goswami, another key figure in the film, offered a different but related perspective. In his seminal work, The Self-Aware Universe, Goswami posited that consciousness is the ground of all being, a philosophical stance claiming that matter arises from consciousness rather than the other way around. Goswami interprets quantum measurement as an irreversible act that occurs in consciousness itself. He thus flips the script of traditional science, proposing that if consciousness were not present, the wave function would not collapse, leaving quantum possibilities in a kind of limbo. Such a position extends well beyond the minimalistic approach of the Copenhagen interpretation, prompting lively debates within the scientific community. It straddles the line between physics and metaphysics, attracting both interest and skepticism. To fully appreciate how, what the bleep do we know, propelled the Double Slit Experiment into the cultural spotlight, one must consider the film's format. It interwove documentary interviews with dramatized sequences. The latter followed the life of a photographer experiencing a series of personal epiphanies influenced by quantum revelations, making the storyline relatable to everyday struggles and existential questions. Then the film introduced segments featuring Dr. Quantum, an animated figure who takes the viewer on a microscopic journey. It is perhaps one of the most memorable sequences showing Dr. Quantum firing electrons at the double slits. The comedic and straightforward narrative style simplified complex physics, thereby capturing the imaginations of those who might not otherwise engage with quantum mechanics. Many academically trained physicists took issue with the film's approach, arguing that it overplayed the role of consciousness or used quantum mechanics as a justification for New Age spiritual beliefs. Criticisms also extended to the film's alleged conflation of quantum superposition with intangible human experiences, like feelings, relationships, or personal transformations. Regardless, the film undeniably reached a broad audience, inspiring them to learn more about quantum phenomena. Consequently, the Double Slit Experiment, once largely confined to the pages of physics textbooks, gained a quasi-iconic status. It became not only an emblem of quantum strangeness but also, for some, a symbol of untapped mental or spiritual potentials. Moving deeper into the scientific context, it is worth noting that the Double Slit Experiment has been tested with not only photons and electrons, but also heavier particles such as neutrons, atoms, and even complex molecules like buckyballs, C60, and small biological molecules. Each time, scientists observed the interference pattern when no path information was available, underscoring that quantum effects extend beyond the smallest fundamental particles. These sophisticated experiments often rely on elaborate vacuum chambers, state-of-the-art lasers for cooling, and finely tuned detectors to minimize decoherence, environmental interference that effectively measures the system and kills the superposition. As the size of the quantum object increases, maintaining coherence becomes more challenging. Yet each successful demonstration reveals that the quantum world's wave-like behavior is not reserved solely for the realm of the very tiny. It is a pervasive aspect of nature that classical instincts fail to capture. One might then wonder, if large molecules exhibit interference under carefully controlled conditions, Why do we not see tennis balls or airplanes interfering like waves in everyday life? The short answer lies in decoherence. In any realistic macroscale environment, countless interactions occur with surrounding particles, air molecules, photons, etc. Each interaction can measure some aspect of the object's wave function, causing rapid collapse of coherence. Thus, while quantum theory applies universally, macroscopic objects appear to behave classically because of the immense complexity of interactions. This phenomenon does not nullify the fundamental lessons of the double slit experiment. Rather, it highlights the extraordinary lengths one must go to preserve quantum behavior in large systems, reinforcing that measurement and environment are crucial in shaping observable outcomes. Returning to the question of the observer's role, we can address the controversies that swirl around interpretations. The Copenhagen interpretation remains the most common approach taught in undergraduate physics courses. It holds that quantum mechanics is a predictive tool, and that collapse is simply a formal statement about when superpositions give way to definite outcomes. Any measuring device, be it conscious or not, can cause the collapse by interacting with the quantum system. For the standard physicist, consciousness itself is not singled out in the equations. Rather, it is an emergent phenomenon riding on top of physical processes. Yet for Fred Alan Wolf, Amit Goswami, and some other thinkers, the observer is not merely a passive participant, but an active shaper of reality. They stand on the shoulders of earlier pioneers like John von Neumann and Eugene Wigner, who contemplated the idea that consciousness might be relevant in measurement. Von Neumann's mathematical formalism put forth a chain of measurement devices. If the wave function collapses upon interaction with one measuring device, but that device itself can be considered quantum, then perhaps we need to place the boundary of collapse elsewhere, eventually pointing to the conscious observer as the only fundamentally unique vantage point. Wigner famously proposed the Wigner's friend thought experiment, further complicating the notion of measurement by having another observer measure the first observer. The scenario raised paradoxes about where and when the collapse occurs. These musings opened the door for more radical claims like Goswami's consciousness creates reality, though such interpretations remain highly debated and are not part of mainstream physics teaching. Since the film What the Bleep Do We Know was released, numerous critics have pointed out that the standard quantum mechanical equations work perfectly well without invoking a conscious observer in any privileged sense. The mathematics of wave functions, operators, and measurement probabilities do not explicitly reference consciousness. Hence, the mainstream scientific stance is that while quantum mechanics undeniably challenges classical notions of reality, one cannot straightforwardly conclude that human thought alone shapes external events. A measurement is often described by a Hamiltonian interaction between a system and a measuring apparatus, resulting in an entangled state that leads to decoherence when environmental degrees of freedom become involved. This picture, advanced by such fields as decoherence theory and quantum information science, provides a more physically grounded explanation of why the wave function appears to collapse. On the other hand, the popularity of quantum interpretations that emphasize the mind is partly due to the extraordinary nature of quantum phenomena. Human intuition has evolved for a world of mid-sized objects traveling at speeds much slower than the speed of light, and quantum effects rarely intrude into our direct experience. Thus, when confronted with the weirdness of entanglement, superposition, and delayed choice experiments, people seek conceptual frameworks that can incorporate elements of subjective experience, our sense of free will, the uniqueness of consciousness, or the ephemeral nature of observation. Films like What the Bleep Do We Know cater to this desire, weaving together scientific and metaphysical narratives that question the boundary between mind and matter. A compelling question emerges from these debates. Does quantum mechanics truly require the presence of a conscious observer to make sense of the double slit experiment's outcome? Or is it merely the presence of a measuring apparatus, conscious or otherwise, that suffices? The experiments themselves do not distinguish between a conscious observer and a non-conscious measuring device. If a photodetector or some other instrument is placed to record which slit the particle goes through, the interference pattern disappears. The presence of a human observer is not strictly required in these experiments to cause the disappearance of the pattern. Indeed, the wave function's collapse or decoherence is triggered once path information becomes irreversibly available to the environment. This suggests that consciousness is not the special ingredient in typical laboratory contexts. Nevertheless, for those who adhere to interpretations linking consciousness and quantum phenomena, the story goes deeper. They argue that no measurement is truly complete until someone becomes aware of the result. An unconscious measuring device, they contend, merely creates a superposition of device states. Only when a mind becomes aware do we get a single outcome. From a purely scientific methodology, this claim is often seen as unfalsifiable, because it is difficult to conceive of an experiment that can conclusively differentiate between collapse due to mind and collapse due to an interaction with a measuring apparatus. Philosophers of science sometimes label such positions as interpretive leaps, bridging physical data and metaphysical assumptions. In the broader realm of quantum foundations, the double slit experiment acts as a microcosm of all these interpretational challenges. It is no exaggeration to say that just about every question one can pose about quantum mechanics eventually circles back to the basic puzzle of how a single entity can exhibit wave-like interference under certain conditions and particle-like localization under others. And more puzzling still, how the act of obtaining information about the path effectively changes the phenomenon from interference to localized scattering. This puzzle has been extended to imaginative new experiments, such as the delayed choice quantum eraser, where the decision to measure which path the particle took can be delayed until after the particle has passed through the slits, yet the results still align with quantum predictions. The consistent outcome: acquiring path information kills interference, while erasing that path information recovers interference. A robust discussion of the double slit experiment must also acknowledge Richard Feynman, whose Feynman lectures on physics remain a masterwork of scientific exposition. Feynman famously declared that the double slit experiment encapsulates the central mystery of quantum mechanics. He insisted that if one fully grasps the nuances of this experiment, they can grasp the essence of quantum mechanics. Feynman described how, when electrons are shot one at a time, each electron seemingly has no knowledge of where the others landed. Yet, collectively, they build up an interference pattern that only emerges statistically after many trials. For him, no classical mechanism can convincingly explain how each electron knows how to align itself to form such a pattern without referencing the wave function's probability amplitudes. Feynman's words continue to serve as a clarion call to every generation of students, reminding them that quantum mechanics is less about certainties and more about probabilities, all the while cautioning against any illusions of truly understanding it in classical terms. Beyond Feynman, other authors have contributed significant expositions on the double slit experiment and wave-particle duality. John Gribbin's In Search of Schrödinger's Cat offers a historical approach to the quantum revolution, including Young's original demonstration and the subsequent experiments with electrons. Bruce Rosenblum and Fred Kuttner, in Quantum Enigma, Physics Encounters Consciousness, delve into the interpretive controversies, acknowledging how mainstream science addresses quantum phenomena and exploring why it so often ignites discussions about mind and reality. These works strike a balance between scientific rigor and readability for the interested layperson, something that What the Bleep Do We Know attempts as well, albeit with a more adventurous philosophical spin. To place the debate in a broader framework, it can be helpful to compare quantum mechanics with classical physics. Classical physics, built on Newton's laws, Maxwell's equations, and the deterministic worldview, is well suited for macroscopic systems. Objects have definite positions and momenta, and one can predict their future states given initial conditions. But quantum mechanics, especially as illustrated by the double slit experiment, reveals that at a fundamental level, certainty gives way to probability, wave functions, and the principle of superposition. This leap from a deterministic universe to a probabilistic one challenges the assumption that nature can be fully described by definite states independent of measurement. Herein lies the philosophical potency of quantum theory, making it ripe for interpretation by those seeking deeper meaning in physical reality. Back in the realm of what the bleep do we know, the film does a commendable job of bringing these concepts, superposition, uncertainty, measurement, to an uninitiated audience. It uses dramatization to depict how these mysterious principles might weave into the fabric of everyday life. From the protagonist's perspective, it implies that one's beliefs or observations could shape personal reality. The film's critics argue that this oversimplification conflates the rigorous results of quantum experiments with the complexities of human psychology. Proponents reply that the film only offers a metaphor, and that it is a creative exploration of the quantum world's philosophical ramifications, never claiming to be a strict educational documentary. Dr. Quantum, the animated guide in the film, stands out as a prime example of how difficult it can be to communicate quantum ideas to the public. His simple demonstration of electrons interfering with themselves is scientifically accurate in a broad sense. If no measurement device is present to ascertain which slit the electron passes through, the electron exhibits an interference pattern. However, the commentary that attributes the wave function's collapse to the electron seeing the observer or knowing it's being watched can be misleading if interpreted literally. From a purely physics standpoint, the electron is not conscious. Rather, the detection apparatus interacts with the electron's wave function, extracting path information, and thereby altering the system's subsequent evolution. Nonetheless, the personification resonates with audiences, helping them visualize the bizarre nature of quantum phenomena. In a pedagogical sense, the cartoon is an effective, albeit simplified, storytelling tool. Over the years, additional research developments have further elaborated the interplay between measurement and interference. The concept of weak measurements, for instance, allows one to glean partial information about a particle's path without fully destroying the interference pattern. Such experiments, detailed in publications like Physical Review Letters and Nature Physics, show that there is a continuum of measurement strengths. Not every attempt to measure path information yields a clean particle-like result or a clean wave-like result. Instead, one can observe partial interference patterns that degrade in proportion to how strongly the experimenter tries to ascertain the path. These results reinforce the principle that measurement is an interaction with the quantum system, and the more information gained, the more the wave nature is lost. The enthralling aspect of quantum mechanics and of the double slit experiment in particular is that it continues to be a subject of both empirical research and philosophical debate. Even though quantum theory boasts predictive success of remarkable precision, fundamental questions linger about the nature of reality itself. Is there an objective reality independent of observation, or is reality always entangled with the observer? While mainstream physics tends to adopt a pragmatic, shut up and calculate stance, focusing on predictions and technological applications, others, including Goswami and Wolf, see an opportunity to unify science with consciousness, spirituality, or metaphysics. Such discussions often branch out into territory like parapsychology or noetic sciences. For example, Dean Radin and other researchers at the Institute of Noetic Sciences have explored whether the mind could have a direct influence on quantum systems, experiments that are not widely accepted in mainstream physics journals. Critics highlight methodological flaws and argue that these claims do not replicate consistently under controlled conditions. But the mere existence of these studies testifies to the allure of the idea that quantum mechanics might open a gateway to scientifically grounding notions of mind-matter interaction. From a more conventional standpoint, quantum information theory has taken the question of measurement from a new angle. Researchers see quantum states not merely as physical wave functions, but as carriers of information. In quantum computing, qubits can exist in superpositions of states, and interference is crucial for quantum algorithms that surpass classical computational limits. Here, measurement corresponds to extracting classical information from a quantum system, collapsing the superposition of qubits into definite states. While quantum computing does not necessarily solve the philosophical debates about consciousness or wave function collapse, it does underscore that quantum phenomena can be harnessed for practical tasks, cementing their existence as real physical processes rather than ephemeral ideas. Reflecting on the enduring appeal of the double slit experiment, one might conclude that it thrives on contradiction. It is beautifully simple in its design, yet complex in its implications. A single barrier with two slits, a detector screen, and a beam of quantum objects highlight an entire cosmos of questions about knowledge, reality, and existence. On a purely physical level, it demonstrates wave-like interference. On a philosophical level, it tantalizes us with the possibility that our active observation shapes outcomes. In pop culture, it has become emblematic of quantum strangeness, partly due to the imaginative depictions in works like What the Bleep Do We Know?, where scientific fact merges with philosophical speculation. To piece all these lines of thought together into a coherent narrative, consider the following key thematic threads that weave through the double slit experiment story. Wave-particle duality, historically established by Thomas Young's demonstration with light, confirmed later by electron diffraction and extended to large molecules. Quantum revolution, sparked by Planck, Einstein, Bohr, Heisenberg, and Schrödinger, this movement shattered classical determinism, ushering in a world governed by probability amplitudes and uncertainty. Measurement problem. The double slit scenario brings to the forefront the mystery of how measuring a quantum system, or simply knowing path information, transforms superpositions into definite outcomes. Interpretations galore. Copenhagen, many worlds, de Broglie-Bohm, and consciousness-centric interpretations reflect humanity's struggle to interpret the mathematics and phenomena of quantum theory. Cultural impact. Films like What the Bleep Do We Know? Popularize these quantum mysteries, though at times blurring the boundaries between rigorous science and speculative metaphysics. Technological frontier. Quantum computing and information theory demonstrate the pragmatic value of embracing quantum principles and measurement rules to create novel applications. A major reason the double slit experiment has retained such a firm grip on our collective curiosity is that it calls into question the everyday logic we apply to the world around us. We are used to thinking that things either happen or do not happen, that an object either goes through one slit or the other. But quantum mechanics is not constrained by such binary categories until forced to be. This puzzling departure from classical reasoning leads naturally to bigger questions. If the quantum realm is foundational for the entire universe, might it be that the everyday world is just a limit or approximation of a far more nuanced underlying reality? Could the observer be intricately embedded in that reality? And if so, what does that imply for how we think about mind, free will, and the nature of existence? In the spirit of a narrative, imagine how these questions might arise in a deeply personal context. A curious individual, perhaps like the protagonist in What the Bleep Do We Know?, observes their life through the lens of quantum metaphor. Every choice, every possibility, is in superposition until they observe or decide upon a path. While from a strict scientific perspective, there is a risk of oversimplifying quantum mechanics. The metaphor captures an essence of newness, possibility, and the power of observation. The double slit experiment then becomes a symbol for how our awareness might shift outcomes. Even if it is not literally the same phenomenon, the psychological resonance is undeniable. Returning to the film's experts, Fred Alan Wolf often emphasizes the shift from a classical worldview to a quantum one, urging us to embrace uncertainty and possibility. Amit Goswami's line of thinking goes one step further, positing that the universe is fundamentally mental. Though such claims remain at odds with the mainstream consensus, they inspire audiences to reflect on the meaning of measurement and the nature of reality, questions that conventional science seldom addresses in a direct, philosophical manner. For a portion of the public, these ideas fill a spiritual or existential gap that purely materialist frameworks do not satisfy. The debate, however, need not be framed as a binary clash between hard science and metaphysics. One might view the double slit experiment as a gateway to multiple layers of inquiry. On one layer, it is about collecting empirical data. How do electrons form interference patterns, and under what circumstances do they behave particle-like? That question can be answered through rigorous experimentation. On another layer, it is about how to interpret that data in a way that is consistent with the rest of physics, but also with broader philosophical stances on reality. Here, the path splits. The Copenhagen interpretation avoids deep metaphysical commitments, while consciousness-centric interpretations adopt them. A third layer might be ethical, spiritual, or even psychological, asking if quantum mechanics offers any practical wisdom or worldview that helps us navigate our human experiences. Films like What the Bleep Do We Know? Dwell predominantly in this third layer, tying the quantum puzzle to personal and spiritual transformation. Regardless of where one stands in these debates, the double slit experiment remains a perennial teaching tool and a wellspring of wonder. Physics students replicate the experiment with lasers and slits as an introduction to interference and diffraction. Advanced labs may perform electron diffraction experiments demonstrating that matter waves behave just like light waves in many respects. Researchers push the envelope, seeking interference in larger and larger systems, testing the limits of quantum coherence. Meanwhile, philosophers and theologians reference the experiment as a case study in how scientific findings can shape or challenge worldviews. And popular media continues to portray it, sometimes accurately, sometimes in ways that deviate from rigorous science, but always in a manner that captures the imagination. If there is a unifying lesson to be drawn from the centuries of inquiry that started with Jung's bright and dark fringes, it might be that nature is more subtle, layered, and mysterious than our immediate perceptions would suggest. The double slit experiment compels us to revisit core assumptions about how the universe operates. Whether one sees it as evidence of wave-particle duality or as a portal into an observer-dependent reality, the experiment confronts us with the challenge of reconciling what is measured with what is assumed. Far from being a mere puzzle, it stands as a testament to the unending human quest for understanding. A quest that merges logic, empirical testing, philosophical reflection, and sometimes, in works like What the Bleep Do We Know?, imaginative storytelling. Thus, in concluding this expansive narrative, we see how a single, relatively straightforward setup, a barrier with two slits, a quantum source, and a screen, reverberates through physics, philosophy, and public consciousness. The double slit experiment has not only confirmed fundamental properties of light and matter, but has also become a rallying point for larger conversations about the role of the observer, the nature of consciousness, and the limits of scientific explanation. Films like What the Bleep Do We Know? Amplify this conversation, illustrating both the power and the pitfalls of blending hard science with metaphysical speculation. Whether one sides with the mainstream scientific establishment, adopting a more standard interpretation of quantum mechanics, or resonates with the likes of Goswami and Wolff, proposing that mind shapes matter, the double slit experiment remains an undeniable catalyst for thought. It invites each new generation to wonder how, precisely, reality is woven from waves of possibility and molded by the instruments and minds that observe it. In essence, the narrative of the double slit experiment is not merely about electrons striking a screen in a lab. It is about the quest to understand what it means to measure, to observe, and even to exist. From Thomas Young's initial demonstration and the wave-like fringes that challenged Newtonian corpuscular theories, to the modern quantum mechanical framework that forces us to accept paradoxes at the core of reality, the journey is as much philosophical as it is scientific. The cultural zeitgeist surrounding this experiment, exemplified by the cinematic dramatization in What the Bleep Do We Know?, testifies to its profoundly evocative nature. It remains one of the best-known illustrations of quantum weirdness, an emblem of how surprising the universe can be when we peel back the layers of the familiar. And it endures because it speaks to a fundamental human curiosity, to seek the patterns hidden in the light and shadows, to ask questions that reveal the deep interplay between knowledge, observer, and observed, and to wonder whether, in the grand interplay of wave functions, we too are entangled in the dance of reality. And so we end our journey through the fascinating double slit experiment, where light, electrons, and even large molecules show us that reality can be much more complex than we imagine. From Thomas Young's ideas to modern quantum interpretations, including the inspiring look of thinkers like Fred Alan Wolf and Amit Goswami, we realize that there is always something new to discover in the universe. If this content aroused your curiosity, like, share, and tell us in the comments what intrigues you most in this quantum world. See you in the next video.